Hello everyone, welcome to this presentation entitled Introduction to LED Lighting and Drivers. This is the third video in this series. In the two previous videos we have seen an introduction to LED lighting and drivers. We have talked about LED lamps structure and operation. We have also seen how to supply the LED lamp from a DC source. And today we are going to talk about offline power supplies for LED lamps. If you are interested in this topic, I recommend you to take a look at my book LED Lighting and Drivers, available from Amazon KDP. So here we can see the typical diagram of an offline LED driver. We have the AC mains. We usually employ a rectifier in order to provide a DC voltage to the main offline LED driver block, which is shown here. And then we have the LEDs, which can be in different arrays in order to implement the lamp. Usually we are going to operate in closed loop by measuring the current through the lamp and regulating the current against the variations of the input voltage here at the mains, and also against variation of the lamp itself. So what are the basic functions of an offline LED driver? We are summarizing here these functions. It is necessary to provide an adequate input power factor and current harmonic distortion at the input of the LED driver. Also, to provide constant current through the LED strings in order to keep the light coming out from the lamp stable. It's interesting also to have the possibility of dimming so that we can change the lighting level coming out from the lamp. We usually need isolation in order to avoid electric shock with the user. We are also interested in having a high reliability, so electrolytic capacitors are usually avoided in this type of converters in order to keep a high lifetime of the LED driver. And of course, we are interested in having a high efficiency. Usually the target efficiency is 90% with a minimum value of 80% within the whole range of operation. And what are the typical converter structures that we use when implementing an offline LED driver? We have in principle three possibilities. The first possibility is to use a single stage converter that is going to perform all the functions, meaning that it has to provide a good behavior at the input with a high power factor and low current harmonic distortion, and also to regulate the current through the LEDs. The second solution is to use a multi-stage converter with 2 stages or 3 stages even, in order to improve the behavior from the input and also from the output, trying to use specialized converters for each function. And finally, we have the third possibility, which is the use of integrated two-stage converters, trying to reduce the cost and the complexity of the converter while keeping good characteristics of the driver at both the input and the output. When working with offline LED drivers, it's also important to know the different standards that are related to this equipment. One of the most relevant standards is this one, the IEC 61003-2, which limits the harmonic current emissions in equipment with input current below 16 amperes per phase. So this standard classifies the different equipment into 4 different classes. We have the class A for balanced 3-phase equipment, household appliances, tools, dimmers for incandescent lamps, audio equipment, and so on. We have class B for portable tools, arc welding equipment. And then we have class C, which is related to lighting equipment and is the class that we have to consider for LED drivers. Finally, we have class D, which is related to specific equipment like personal computers, TV sets, and so on. For the class C, the standard has different limits depending on the power of the lamp. So for power ratings in between 5 watts and 25 watts, which is the typical case of light bulbs, as we can see here, we have 3 different options to satisfy the standard. And below 5 watts, we don't have any limits in this standard. And then we have another range for power rating higher than 25 watts, which is the typical application of higher powers in outdoor lightings. Let's see as an example the case of active power higher than 25 watts. We have this table here with the different limits, and what we have to do is to measure the different harmonics of the current from the second harmonic to the 39th harmonics, only the odd harmonics from the 11th to the 39th harmonic, and then this is the maximum value of each harmonic as a percentage of the input current at the fundamental harmonic. So for example, the second harmonic has to be lower than 2% of the amplitude of the fundamental harmonic. In the case of the third harmonic, it has to be lower than the percentage obtained by multiplying 30 times lambda, being lambda the power factor of the converter. And for the rest of the harmonics, we have these percentages here. Here we can see the typical laboratory equipment that we can use to do this kind of measurement. We have the power supply here to emulate the grid, and then we use a power analyzer to measure the current absorbed by the converter, and also to measure the voltage, so the power analyzer can do all the measurements. It can measure the power absorbed by the converter and also to analyze the current waveform in order to calculate the amplitude of each harmonic. We can connect also a computer to do all the representations and analysis. And here we can see an example of a report in which in blue we can see the amplitudes of the different harmonics of the current, and in red we have the limits corresponding to each harmonic in the standard. So we can see that there is no limit, of course, for the fundamental harmonic, and then we have these peaks corresponding to the maximum values of the current at each harmonic. Other interesting standard, so to speak, is the Energy Star, which is a voluntary program of the US Environmental Protection Agency, and it also proposes different characteristics for products like LED bulbs. So we can see here different regulations proposed by this program. For example, regulates the correlated color temperature of the LED bulbs with these nominal values, the color maintenance, the color quality, and so on. So we have different characteristics for the light bulbs. Regarding the supplying related to the LED driver, for the case of the power factor, we have that for light bulbs with a power lower than 5 watts, there is no limit, and for powers higher than 5 watts, the power factor must be at least 0.7. Also, the LED operating frequency has to be higher than 120 Hz and so on. So we can get more information about this program following this link here. Another interesting standard related to LED drivers is the IEEE 1789 of 2015, which is entitled Recommended Practices for Modulating Currents in High Brightness LEDs for Mitigating Health Risks to Viewers. So this standard regulates the value of the modulation in percentage here as a function of the frequency of operation. So if we have a current circulating through the LED like this one, we have an average value, and then we have a ripple, we have a maximum value of the current and a minimum value of the current. We are assuming that the current is proportional to the light intensity, and then we can calculate the percentage of the modulation using this expression here. So the standard what proposes is to have always a value of the modulation percentage in this recommended area. So it has to be below these values here, in order to minimize the visual discomfort and annoyance to the user, and also to provide low risk for headaches and photosensitive epileptic seizures. So let's start now with the different LED driver configurations. We can see here the three possibilities that we have seen before. The first one is to use a single stage to implement both functions, the power factor correction and also the regulation of the current through the LEDs. These are some of the features of this possibility. It is simple, it provides good efficiency because we have only one stage, but the problem is that we are going to need large bulk capacitors to get low current ripple through the LED. And also the dynamics is going to be slow because of using these very high capacitors. So the second possibility is to use a two-stage converter, in which we use one converter or one stage for implementing the power factor correction, and then another stage for implementing the driving of the LEDs and the regulation of the current. This is in principle better because we have two independent controls for each of the functions. It provides also better design flexibility because we can design both stages separately. The second stage can do also part of the regulation against input voltage variation, so we can reduce the bulk capacitance and therefore we can get a fast dynamics. But the problem is that we have a much more complex converter with control circuitry, and therefore the cost is going to be higher. So the third possibility is to employ integrated two-stage converters, in which we are going to integrate both converters, the power factor correction converter and the LED driver, in a single stage converter with a lower number of components and simpler control circuitry. So this type of converters can be simple. We can reduce the value of the bulk capacitance, we can provide fast dynamics, and also we can reduce cost. So let's see now an example of a single stage converter used as an LED driver. In this case, we are proposing a buck boost converter for this type of application. We have a line voltage of 230 volts and 50 Hz. The LED lamps is 200 volts and 0.35 amperes, and the selected switching frequency is equal to 50 kHz. So calculating the inductor for this application, we require 0.9 millihenries. And then we have selected here an output capacitor of 130 microfarads. So with this capacitor, the waveforms are shown here. These are simulation waveforms. This is the lamp voltage with an average value of 200 volts. and then we have the lamp current with an average value of 350 milliamperes and a peak-to-peak ripple of 0.1 amperes. So we can see that we need quite high value of the output capacitance, 130 microfarads, to get a quite high current ripple of around 30% of the average current. So usually electrolytic capacitors are employed in these kind of applications because they are cheap, they are compact, they can get a high value of capacitance in reduced volume. But the problem is that the lifetime specifications for electrolytic capacitors operating at a maximum core temperature are usually between 1000 hours and 10,000 hours, while LED lamps can reach a lifetime up to 100,000 hours, as we know. So we need to avoid the use of electrolytic capacitors in this kind of applications because otherwise it's going to fail the driver before the lamp itself. Also, another disadvantage of using electrolytic capacitors is the high series resistance that we have in this kind of technology compared with other technologies like film capacitors or ceramic capacitors. So we are going to have higher losses also in electrolytic capacitors, and the efficiency of our LED driver is going to be lower. The reason of the low lifetime of an electrolytic capacitor is that they use an electrolyte, a liquid inside the capacitor, to improve the capacitance over volume ratio, and this electrolyte is going to evaporate as the capacitor is aging. So the evaporation of the electrolyte depends at the end on the temperature of the electrolyte, and this depends on two factors. One is the operating ambient temperature and the other one is the alternating current circulating through the capacitor itself, because at the end this alternating current is going to produce losses in the series resistance of the capacitor, and then the temperature is going to increase. So these are the typical characteristics of lifetime of an electrolytic capacitor, where we have here the values of the lifetimes as a function of the operating temperature and as a function of the alternating current. So the higher the alternating current, as we can see, the lower the lifetime, and also the higher the operating temperature, the lower the lifetime of the capacitor. However, film capacitors or ceramic capacitors do not have a liquid inside. They employ only solids inside the structure, and therefore the lifetime is much higher. So one solution that we have seen to reduce the value of the bulk capacitor is to use two separate converters in order to implement the LED driver. We use one converter to implement the power factor correction stage, and then another converter, a DC-DC converter, to drive the lamp in closed loop. So this second converter can compensate variations of the voltage across the bulk capacitor, and then we can reduce the value of this bulk capacitor for a given current ripple through the LED. We know that this is complex, we need more components, more integrated circuits, and so on. So one possibility to reduce cost and complexity is to integrate both stages in only one stage that we call integrated stage. In this way, we are going to have the same functions as in the case of the two-stage converter, but with some, of course, some disadvantages. So this is a summary here of the features. What we do is to share the control switches between both stages in only one stage. With this we can provide simpler circuitry and lower cost, but of course we are going to have less design flexibility because both converters that are integrated must operate with the same switching frequency and duty cycle. So this is one disadvantage. And there is another disadvantage, which is that we are going to have higher stress of voltage and current in the shared switch. However, in terms of efficiency, the integrated stage solution is going to have similar efficiency as the two-stage solution. So let's see now an example of an integrated converter used as an LED driver. Here we have the first stage, which corresponds to a buck boost converter. We use here a buck boost converter because with a buck boost converter we can provide automatically power factor correction when the converter operates in discontinuous conduction mode. And also we can get an output voltage that can be higher or lower than the input voltage, so this is very flexible. And then we are going to add as a second stage another buck boost converter as shown here. This second stage is going to correct the sign inversion of the first stage, because here we have the positive voltage at this point, negative voltage at this point. So we are going to have now positive voltage here and negative voltage here, which is more convenient. And this second stage, in principle, can operate in both discontinuous conduction mode or continuous conduction mode, but it can be demonstrated that if we operate the second stage in discontinuous conduction mode, we can further reduce the ripple through the LED lamp, and therefore we can attain a lower value of the bulk capacitance for the same output ripple. Now the idea is that we can integrate the two stages in only one by sharing the operation of the two switches, this first switch of the power factor correction stage and this second switch of the DC-DC converter, using only one switch to perform both functions, so that we can use only one control circuit for the whole converter. For the integration of switches in power converters, there is a methodology that we are going to skip here to keep this video short, but here we can see the resulting topology. So we are using only one switch and one here, and we need to add an additional diode D2 here to implement the operation of both converters using only one control switch. So when the switch N1 is closed, we are charging the inductor LE in this way, and also we are charging inductor LO in this way here. And when the switch is open, then the energy of the inductors goes into capacitor CV, the bulk capacitor, in this net here, and also the energy of the output inductor here goes into the output following this circuit here. So let's see now some laboratory implementation. Here is the lamp that we have implemented for testing these converters. Is the same that we have used also in the single stage converter shown in previous slides. We have used 60 LEDs. The total power rating is 70 watts. The voltage and current is 200 volts, 350 milliamperes. Total luminous flux 1500 lumen, and the equivalent circuit is as shown here with a voltage threshold of 170 volts and series resistance of 87 ohms. And this is the laboratory implementation of the prototype. Here we have the schematic. We are measuring the current through the lamp using a series resistance and sending this information to a filter and then to a compensator implemented with operational transconductance amplifier that is included in the driver LM3524. And here we have a picture of the prototype with the input inductor, the output inductor, the bulk capacitor here, and the output capacitor here. We have to highlight the value of the bulk capacitance, which is only 12 microfarads for the same output ripple than in the case of the single stage converter that we have seen before. In the single stage converter we were using 130 microfarads, and here we are using only 12 microfarads, so the reduction is considerably. We are dividing by 10 the value of the required capacitance. These are some waveforms measured in this prototype. These are the MOSFET waveforms. We have the drain to source voltage here and the gate to source voltage here at the bottom. We can see that the peak voltage is around 650 volts for the MOSFET, which is higher than in a usual application because of the sharing of the switches, as we have seen. And here we show the bus voltage, which is this waveform here, and then here we have the output voltage. And here we can see other waveforms. In this part we have the voltage applied to the LED driver, and this is the current, so we can see that it is quite sinusoidal. The power factor is 0.99 and the total harmonic distortion is 12%. And on this part here we have the lamp voltage and current. This is the voltage, and here we have the current. So the current, the voltage ripple is around 10 volts peak to peak, and the current ripple is 0.1 amperes peak to peak. And we have measured for this prototype an efficiency of around 86%. But I have to say that we have developed after this prototype other prototypes, and we have gotten around 92% of efficiency already with an improved design. And here we have other examples of integrated converters. For example, here the buck boost converter with the buck boost converter, which is the double buck boost converter that we have just seen. This is the buck boost with a flyback converter, the buck boost with a buck converter, the buck boost with a forward converter. And other examples are the buck converter at the input integrated with a buck boost converter at the output, as shown here, the buck with the flyback, the SEPIC converter integrated with a buck boost converter, and the SEPIC converter integrated with a flyback converter. Well, this is all today in this presentation. Today I want to finish this presentation showing a picture of my campus in Gijón, Campus de Viesques of the University of Oviedo. And here you can see a picture of my beautiful city, Gijón, in Spain. So I hope that you have enjoyed this presentation. Please let me know if you have any comment or question. Thank you very much for watching, and I hope to see you in the next video. Goodbye now.